Now that you understand Ritt's theory, it will be relatively easy for you to understand how finite element modeling works, because Ritt's theory forms the foundation for the finite element method. Now there are some important details that make the finite element method unique and powerful, so let's talk about that. With the Ritz method, we begin with this assumption that the displacement field can be represented as a product of basis functions times their respective amplitudes. We do the exact same thing in the finite element method, only we choose basis functions that have a unit value at one node, so that the amplitude of response at that mode, the amplitude of that basis function is equal to the displacement at that node. And then our basis functions are also local. They exist only over the finite element. So look at this example for a 1D beam. If we're talking about axial deformation of a beam, we have 1 degree of freedom on each node, and we'll plot things as if the motion was vertical just to make it easier. So we would use two basis functions for this finite element model. Psi1, which would have a unit value at node 1, and it would go to 0 at node 2, and then psi2, which has a unit value at node 2 and is 0 at node 1. So because of this property, when we plug in to find into the Ritz series here to find the displacement at each of those nodes, we find that it's equal to the amplitude of the basis function. So that makes our bookkeeping and a lot of things a lot easier. But the real power to the finite element method comes in doing this and breaking a complex structure into lots of elements. So suppose we wanted to find the axial vibration of this structure, a pinned beam. You'd run into problems trying to use the Ritz series because your basis functions would be continuous over the whole structure, and it'd be difficult to deal with this discontinuity there. You'd need a lot of basis functions before you could really accurately capture that discontinuity. With the finite element method, the basis functions would be local. So if this was our first element, our first basis function would look like this, the next two like that. So our first finite element would have 2 nodes, and then the second would be spanned here, and so on along the length of the beam. And so these can easily be placed such that we put this discontinuity right between 2 elements, and we can capture it more effectively, probably. This also makes bookkeeping and importing loads and lots of things easier than with the Ritz series. So this is a 1D example. Most of the systems we're interested in have bending, so we need to add to those axial displacements bending displacements. And for the bending to be continuous, we also need to look at the derivative, or the slope. A beam can carry load due to the slope and due to the deflection. So a beam element would need to have 3 degrees of freedom per node like this. So we would take an element like this, and if we assembled a finite element model with beam elements, we would get mass and stiffness and damping matrices just as we do with the Ritz series. Only our displacement vector, rather than being amplitude of global basis functions, it would be the displacements of nodes. And only internally in the code would we realize that this mapping was going on, that we're assuming a certain continuity of the displacement field between the nodes. Okay, so our displacement vector then would have the displacements and rotation of node 1, the same for node 2, and so on. And so we'll need to do some kind of bookkeeping to keep track of where all the different items of interest are. One way to do this is with a DOF vector. So DOF is defined as the node, and then the decimal has the direction. Also, you can do this with 2 columns, one for the node number and one for the direction number. That's probably more effective and maybe what's done more often now. This is nice because it gives a 1 by n vector. But in any event, so here we'd have node 1, the 1, 2, and 6 directions. So if we have a coordinate system x, y, z coming out, u is the x displacement, w is the y displacement, and theta would be the rotation about z. So those are 1, 2, 6, and then we'd have the same thing for node 2. And we could continue on, and we could do this with millions of degrees of freedom and easily search through and keep track of where different nodes are and how to pull out the items of interest. Here are some MATLAB code examples. For example, if we wanted to find the 3 DOF associated with node 10, we could use this command. If we did DOF equals 1 on this vector, we would get 1, 2, 3, telling us that the first 3 indices in DOF or in X are the displacements of interest. If we want to plot a mode shape, say we want to plot the lateral deformation, then we're going to need to grab all of the dot 2 directions, right? And so we can start at the second one and skip 3, or we can do another find command, as you see down there. So this can be really powerful and a good way to track down displacements in a complicated model with thousands of degrees of freedom. All right, let's look at an example. And to do this, rather than using a commercial package, I'll just use a simple MATLAB code so that you can see the guts of everything if you want to. And we can do this in a familiar environment with a minimal of learning that we have to do to get up to speed. So our goal will be to model this beam. Ignore the cantilever part there, that's a typo. This is the free beam. It's sitting on foam, and we assume that the stiffness of the foam is negligible. And the beam is a 1/2 by 1 inch rectangular cross section, 40 inches long. So we will simulate this beam and try to estimate its modes of vibration. And then we'll also simulate the sound we might get if we hit the beam on the center versus hitting it on the end, and we'll compare that to some actual measurements. So let's switch over to MATLAB here. Here is the code that we would need to create this finite element model. So we just need to define all of the properties of the beam, the material properties, the dimensions, the length. One important thing to remember, if we put the density in pounds per inch, 0.2 pounds per inch for steel, or per cubic inch, then we have to divide that by gravity in slinches to get the units to work out. But anyway, we plug all of that in, and then this function has all of the finite element machinery built in, and it spits out stiffness and mass matrices for the beam with the number of nodes that we specify, and also this vector which tells us the coordinates of those nodes. So let's run this far and see what happens. So out comes a picture, a plot of the first 3 elastic mode shapes. And those look as we'd expect. They look a lot like the analytical ones. If we look at the command window here, these are the natural frequencies it found. It found 3 rigid body modes. It ran into a little bit of numerical trouble and made these first 2 complex. And then all of the elastic modes have these natural frequencies in hertz. For reference, I calculated the first natural frequency using the equations in the back of Ginsberg's book, and it matches to 4 significant figures, almost 5. So we get a very accurate answer with just 30 elements. Now these matrices, K and M, look, these are 93 by 93. One way you can see the matrix is to use the SPY command. So this shows you the matrix that we get for the stiffness matrix and the coupling between the nodes. And it's banded because node 1 doesn't isn't connected directly to node 30 and so on. But node 1, DOF1, is connected to DOF6 because, as we saw, those are on the same finite element. All right, so anyway, with a relatively small model, this is small by today's standards, we got the solution in a fraction of a second in MATLAB, we can get highly accurate results, nearly as good as an analytical solution. All right, let's run this again and just get our mode shapes back. So now let's look at what happens if we calculate the sound generated. Now we could use and integrate the full model, the full 93 by 93 model, but the highest natural frequencies would be very noisy. Let's just, for example, let's add one to the plot here. We'll just do a line, and let's take the last mode. And we'll make it black so we can tell it from the rest. And here's the last mode. Basically has a kind of a crazy motion of just the ends of the beam and nothing happening in between, right? So that's pretty strange. We could take the second to last and just see another example. So anyway, those modes aren't very meaningful, and they could actually contaminate the result if we try to integrate. So what I'm going to do instead is just use the first 30 modes and do a modal solution. So we'll specify the initial displacement. I'm going to say that the initial velocity of the first node is 1. So the idea is that if we hit the beam here with an impact, we would change the velocity of this node instantaneously. All the others would have a 0 initial velocity. And then we'll convert that into the modal amplitude of all of the 30 modes of interest. And then here I'm just calculating the natural frequency damping ratio, damp natural frequency of each mode. So I can plug into our formula for the modal displacement versus time. If we then do that and we calculate the modal displacements, we can multiply by the mode shape matrix to get back the physical displacement at a point. And we'll play that back as a sound and also plot the FFT so we can make sense of that. So let's try that. So that was the sound of the beam being struck on its end, and this is the FFT. And you can see that there are lots of modes that are excited. They're excited in a certain pattern. The amplitude goes down as the mode number goes up. But in any event, that's the sound that the finite element model predicts we should get. Now let's go ahead and save that so that we can compare it with what will happen when we excite on the end. So we'll call that UTD end. And we'll just go up and change this one line and see what happens. Okay, and there's the sound we get when we excite at the center of the beam. And you can tell right away that it's different. Should we compare the FFT first, or should we look at it first? Let's listen to it one more time, and then we'll look at the plot. This is the poor man's way to get these two curves on the same plot. We'll overlay that. And then let's just go back and play those two sounds. So if we play, let's do it this way. So we'll play the sound of the end of the beam, and then the sound at the center of the beam, impacting at the center. Oops, looks like we didn't save that yet. That's the center. End. So we get a kind of a deeper, richer sound when we excite at the end versus when we excite at the center. The center sounds kind of more tinny, huh? So if we look at the FFT, we can try to make a little bit of sense of that. What you see, which you might have guessed, is that when we excite at the center, we miss every other mode. And that's because the even modes all have 0 at the center. So they're not excited by an impact at the center. So we get only the odd modes when we excite it in the center. So we get fewer frequencies, and somehow that contributes to the difference in sound. Let's listen one more time. Middle, end. All right. Now that you've seen the computer simulation, we'll see what happens with the real beam. We will excite it. I'll use a few different methods, and we'll see how the sound compares to what we got from those computer simulations. So first I'll tap with my knuckle, which will not excite so many high frequencies. So if we do the center, you can hear the tone that it makes in the center, and now the end of the beam. A little different mix of frequencies in either case, right? Center, end. And that's because those 2 points excite different modes, a different set of modes. Now we'll try impacting with this elder wand here. And this is a little harder plastic. This will excite some different frequencies. So center versus end. Alright, so there you have the sound from the real beam. Okay, well now you've seen the experiment, and you've seen that we were able to do a reasonable job of predicting the sound that would come when the beam was hit at the center and at the end. Now everything we did was really approximate. To really do this well, we need to account for the transfer function between the vibration of the beam and the radiation of that sound through the air, through the room, and to our ears. So what we did was just really qualitative only, but the sound is actually surprisingly similar. So now that we've done that, I'll show you some more complicated examples. This is a code that one of my former students created that basically takes the beam finite element models that you just saw and puts them together into various shapes. So this first part is identical to what we did. It's just a straight beam. So let's look at this part to see something more interesting. So this is a circle. So it's a bunch of beams arranged into a circle. We get some rigid body modes, and then we get mode shapes that look like this. And these are called ovaling modes. We have the sphere crunching in. And notice that they come in pairs with equal natural frequencies. This is a common thing you see in structures like this. This mode is the same as this one, they're just rotated by 45 degrees. So you see this all the time in rockets and things. And these pairs of modes can be difficult to capture experimentally. In practice, they usually don't end up being at exactly the same frequency because you might have differences in stiffness and mass around the circumference. But anyway, this type of mode is seen in a lot of structures. So you get lots of ovaling type modes, and then finally down here we get the first, what we call a breathing mode, where the whole circle is going simultaneously. And this is interesting, again, because it's relevant to a lot of structures. One example is a rocket engine. This is the J2X engine, similar to a lot of others where there's fuel delivery system and combustion, and then a big nozzle. And the hot gases, after they burn, travel through this nozzle, and that causes them to accelerate. And for those of you who haven't had fluid mechanics, you think of a nozzle on your garden hose as being something that comes to a point to speed the flow up, right? But it turns out that at supersonic speeds, a nozzle actually needs to open to cause the fluid to accelerate. So this shape causes the fluid to accelerate, and we want the highest possible speed of the fluid as it leaves because that'll maximize the thrust that we get from the engine. Well, all kinds of rocket engines such as this can have a problem with lateral forces being exerted by the flow. So the flow coming out of the engine can separate so that you get a higher pressure from the outside atmosphere coming in, or a lower pressure depending on what's happening. And that flow separation can actually be variable with time. And in any event, that basically exerts a side-to-side force or a lateral force on this engine. That can excite bending modes of the rocket engine. It can also excite all of these different types of ovaling modes. So these types of modes are very important, and a lot of engineering and thought goes into the stiffness and the strength of the engine in those, when vibrating in those modes, to make sure that they can survive flight. So, and this was something that was really easy to do with the finite element method. Once we knew how to do one element, it wasn't too hard to put them all together into a ring and describe this complicated shape. So we could look at other examples as well. Here's one that was just kind of for fun, putting a bunch of beams together in a star shape. They're tied together only at the ends, but in any event, you can see the different ways that this combination of beams wants to deform. And looking at these kinds of things, you can learn a lot and start to get a feel for how different structures will move. So a lot of examples we could look at. Last but not least, just for you, I've created a really special finite element model. And here's the model. It's beams arranged in a heart. And you can look and see the vibration modes of a heart.